Hi there. Welcome to the very first video of semester two, sort of a review slash preview of our new unit, which is on right triangles. And so we'll talk about that in just a moment. As part of the do now, we did a review of some exponent rules because exponents are going to come into play. But I'll leave that for a different video or another time. However, these things which are called square roots are important to remember how they work. So if I ask you, what is the square root of 64? What that is asking you is what number times the same number times itself equals 64, right? So the question is, what number times itself equals 64? And if you know your times tables, you know that that number is 8. Because 8 times 8 equals 64, then that means we could say the square root of 64 is 8. But then we had to remind you that you learned in algebra. Also, negative 8 times negative 8, that also equals positive 64. A negative times a negative is a positive. And so really, when we take the square root of a number, we know that there's actually two answers, positive and negative 8. And we could say the same thing about 121, right? That's 11 times 11. It's also negative 11 times negative 11. So positive and negative 11 are the square roots of 121. But this idea that there's both a positive and negative answer is fairly abstract, and it's confined really to just pure mathematics. If you're doing like calculations regarding a thing that you're building or something like that, and you need to do a square root, as we'll see, that might come into play, you wouldn't care about the negative. So I'm going to just not really dwell on that. We're only going to really talk about the positive. So we could just say 8 and 11. The thing about the square root of negative 9, there's stuff that you'll learn about in Algebra 2 that kind of explain, how do you take the square root of a negative number. But in principle, if you do a positive times a positive, because if you're doing a number times itself, if that number is positive, then it's a positive times a positive, the answer is positive. Or if that number is negative, then it's a negative times a negative, and that answer is also positive. So remember that you can't actually take the square root of a negative number. And so if you see a negative number under the square root sign, there's just no answer, because there's no number that when you multiply it by itself, you get a negative answer. And then last but not least is this square root of 51. And so I just wanted to see if folks knew how to estimate. The square root of 49 is 7, because 7 times 7 is 49. And the square root of 64 is 8. We already covered that. 8 times 8 is 64. Well, 51 is between 49 and 64, which means the square root of 51 is between 7 and 8. It's a lot closer to 7 than it is to 8. So some students said it's like 7.1 or 7.2. Both of these are pretty good estimates without doing any sort of scratch work, just thinking, it's pretty close to 49, so the answer should be pretty close to 7. The actual answer, I think, is 7.141429 or something like that. And so, 7.1 would be slightly better, but I just wanted to remind folks that there's a way to find that. So all of that comes into play when we start to learn about right triangles, and this thing that we're learning about called the Pythagorean theorem. So you can copy these notes. Right triangles are special because, first of all, they have a right angle here, and directly across from that right angle is a special line called the hypotenuse. The hypotenuse, it's very important to be able to find it. It is both across from the 90-degree angle, across from, across from 90-degree angle, and it's also the longest of the three sides, the hypotenuse. It's the longest of the three sides. In every right triangle, only in a right triangle with a right angle will you have a hypotenuse. And so we spent some time thinking about that. And then there's this thing called the Pythagorean theorem, which just briefly, there's this guy named Pythagoras, right? He was a Greek guy, and he's credited with the discovery of the theorem, and he did not discover the theorem, all right? So I always have to point out that history doesn't necessarily reflect what actually happened. People in Africa and Asia were using the Pythagorean theorem for, generations, for hundreds of years, maybe even thousands of years before Pythagoras was even born. But because he was the Greek philosopher that sort of wrote it down and put it in a book in a specific way, they named it after him, which isn't very fair. But it does work, and it says the sum of the squares of the legs, each A and B in this diagram are the legs, is equal to the square of the hypotenuse. So A to the second power, A squared, plus B to the second power, this is the sum of the squares of the legs, It's equal to the square of the hypotenuse. So this is the Pythagorean theorem in a nutshell. The one side squared plus another side squared equals the third side squared if that third side is the hypotenuse. Then we did a couple examples, and you can pick these notes up on Schoology, but in this example, the hypotenuse is C. And then we could say that A is 6 centimeters and B is 8 centimeters. So we said A squared plus B squared equals C squared, and we said find C. Well, I used a 6 in place of A, so I do 6 squared. And in place of B, I have an 8, so I do 8 squared. And then I don't know the hypotenuse, so I say that's C squared. 6 to the second power, 6 times 6 is 36. 8 times 8 is 64. And so I'll just keep going. I can actually add these, I think. 36 plus 64 is 100. And so that turns out that the hypotenuse to the second power is 100. And we can't forget that we also have to take the square root. So C is not 100, C is 10, because 10 times 10 is 100. So this is 10 centimeters in length. And that's a very basic use of how one can use the Pythagorean theorem to find a missing side. Let's look at one other example. So this one, the C, in our case, is the longest side. The side across from the 90-degree angle is the 13-inch side. And so I could say that A squared plus 12 squared equals 13 squared. Again, that's just because A squared plus B squared equals C squared. And I decided that C was the 13-inch length. And so then I know that 12 squared is 144. 13 squared is 169. The difference here is that I have the number I'm looking for plus 144. So I have to do a little bit of algebra to solve it. I'm going to subtract 144 from each side like this. And I know that the number squared equals 169, take away 144 is 25. And so A is obviously not 25 inches if this is 13, but if I take the square root, I find that A is 5 inches. Okay, so that's another example of how one finds a missing length using the Pythagorean theorem. And there are several homework problems that I want you to work on in which you're going to sort of practice this process. So you can come back and watch this video if need be. The other thing that we did was we looked at some proofs, and here they are, right? So I'm going to just do them really fast. See this right triangle here? Well, if I take A times A, then I have the area of this red square. And if I take B times B, then I have the area of this square that's hanging off of side B. And if I take those two areas and I rearrange them like this, see how they fit directly inside of C squared? So this is evidence that the area of this square plus the area of this square altogether is equal to this area here. A squared plus B squared equals C squared. We looked at another one like this, where I have an A here and a B here, and there's those two squares next to each other. And when I rearrange it, then they rearrange into this square here that is C squared. And see these blue and red right triangles, those are identical triangles, and A is here and B is here. So that's another proof. And then finally, we had this third one where we have 4 identical right triangles with A and B, and then C, that C squared is there, and that empty space is the area of C squared. And if I rearrange it like this, the empty white space is A squared and B squared together. And so those are 3 different proofs. And then I had this nerd proof where I actually did some algebra that looks like this. I'm not going to go over it. If you're interested, you can ask me and I'll let you know. And so what you should do is look for the Desmos link and try the asynchronous assignment where we're just practicing the stuff that I showed you here. And then next time we'll drill down it a little bit more into how we can use the Pythagorean theorem.